Okay guys, welcome back to part 2 of lecture 2. So now we'll look at some example. In first example 3.1, we need to find the required MMF to produce a given flux density. Okay, we are given the air gap and core length and area. So in our magnetic structure, we can calculate the core reluctance RC and also the air gap reluctance RG. Okay, we know the required flux density is 0.5 Tesla, which is 0.5 Weber per square meter, and we assume that the air gap is 1.1 times larger than the core cross-sectional area. So this is the assumption, and it means that we are considering the fringing. So after calculation, and we know that they are in series, we can calculate the total reluctance and multiply it by the required flux to know the required magnetomotive force, the MMF. So we may have many ways to implement this MMF requirement. We may have just one turn, and then we put through 400 ampere, or we have just 1 ampere, but we are using 400 turns, so we will end up with the same NI, which is a nice feature when you design magnetic structure. It's very flexible for you to do that. And in example 3.2, we need to find the flux through the coils. We have 3 coils in the structure, okay, and all the air gap are the same in length and area, and we also ignore the core reluctance and also ignore the fringing. So basically you have an equivalent circuit with just 3 MMF source like this. We have 3 MMF source, 1, 2, 3, with the same reluctance for all 3 branches. Okay, there are many ways for you to solve this, but if you are applying the nodal method, it would be easier. We can use an intermediate value quantity. We call the MMF between node A and node B F, and therefore we can write 3 equations and end up with this at the KCL for node A or node B, and after that we find out F equal 500. Therefore we can calculate that phi1 and phi3 will have the same value, different sign. It means that phi3 is actually going this way, okay, and there's nothing flowing through the second branch, so phi2 is 0. And now let's talk about mutual inductance. So we know the self-inductance. A coil, when we have a current going through it, is going to create a flux and then flux linkage. And if you divide that flux linkage by the current, then you have some inductance. And because there's only one current, one coil, we call it self-inductance. Okay? Here, mutual inductance is another concept. I have 2 coils. If I put a current through one coil, I may have some induced voltage in another coil. If the current I put through the first coil is varying in time, okay, because we have some induction from the flux created by the first coil into the second coil. So the process in the book is to look at step by step. We assume that we exciting one coil 1, when we have coil 2 open, and then we assume that when we open coil 1 and then excite coil 2, and we can have a lot more. We can have some more equations. Okay, and then finally we excite both coils. Then we have the final expression, which is here. For example, if you look at coil 1, the total flux will be the flux through coil 1 created by coil 1, the flux, okay, in coil 2 created by coil 1, and the flux in coil 1 created by coil 2. So the first two is sum and to give you the total flux created by coil 1, and then this is the flux in coil 1 created by coil 2, similarly for coil 2 here. Okay, so whatever in one coil but created by another coil is related to a mutual inductance. So by definition, if you divide that, if you multiply that phi1 with n1 and then divide it by then you have the flux linkage for coil 1, which is L1 multiplied by I1 and M multiplied by I2. Similarly, for coil 2, what created by I1 will be related to a mutual inductance, and what's related to the coil in that, the current in that coil will be the related to the cell inductance L2. So now if you calculate the time differentiation, which means d by dt of those lambda 1 and lambda 2, you will have V1 and V2, and they will have two components. Okay, one is related to the cell inductance and the other one related to the mutual inductance. Okay, so we define the coupling coefficient of coupling is K. That would be equal M divided by root 2 of L1, L2. Normally, we can prove that K is between 0 and 1. And if you have coil loosely coupled, then K would be less than 0.5. And the tightly coupled coil can have K larger than 0.5 and can approach 1. So here let's have a look at an example. So we are given the reluctance of 3 air gaps in that magnetic circuit. We have to draw the equivalent circuit and then compute the flux linkage and also the inductance. Okay, so we can establish the equivalent circuit with two loops. So the coil here will have R1, and the coil here will have R2. Okay, and the coil here will have R3. No coil here, only R3 in this branch, and we can write the expression. We can write the MMF equation for the loop 1 here, just like we do with the electric circuit. And this is for loop 2, and then we can put a number in. Okay, I put the real value for R1, R2, R3, R2. Okay, R1, R2, R3 in. So I have these equations set up. And now I will solve the equation for phi1 and phi2. So we consider phi1 and phi2 are unknowns for the equation, and then we solve them as expression of I1 and I2. And after we get phi1 and phi2, we multiply phi1 by n1 to have lambda 1, and multiply n2 to phi2 to calculate lambda 2. So here you have an expression with some coefficient related to I1 and some coefficient related to I2. So if you remember, lambda 1, whatever multiplying to I1 will be the L1. So L1 is this value. Okay, whatever is multiplying to I2 in lambda 1 expression would be the M. Okay,